Hey guys, Mr. Gucci here, and this is the video to walk us through the 5.1 notes, which is the chapter on covalent bonding, section on the introduction to bonding. All right, so let's get going on this. Now, we began this discussion with a brief review of something that we talked about a little bit in some of our classes last unit, and that was the idea of valence electrons or valence electrons. These are the electrons in the outermost energy level around the atom. These are its outermost electrons. And every atom must have between 1 and 8 valence electrons. All right. If you try and place a ninth valence electron, that electron will be repelled by the others and it will move out to form a new layer. This is essentially the alpha-bow order that we talked about. How, as you diagonally fill in that alpha-bow chart, you see that the highest energy levels are always going to be either an S or an S and a P. So the most electrons you could have would be 2 electrons in an S and 6 electrons in a P. That's 8. All right. And then if you try and place in the ninth electron, it will go and form another energy level. Okay. Because remember, electrons prefer not to be crowded. Here's a little diagram of it. Okay. So you got your nucleus in the middle. You place your first 2 electrons, energy level filled. All right. Then you start placing your next electrons in the next energy level. And you can place 8 of them before that layer is filled. And then you start filling the third energy level. Now it can hold up to 18. But once you get 8 in place, there is so much repulsive force from these electrons that you will start filling in the next energy level. And after you put a couple here, then you start filling in the level below. But you will only ever have, the point is you will only ever have, at most, 8 outer electrons around the atom. All right, here it is from an electron configuration standpoint, okay? So here's the electron configuration of fluorine, right? 1s2, 2s2, 2p, 5. So in this case, the highest energy level here is the second energy level, the 2s and the 2p. And in total, there are 1, 2, 3, 4, 5, 6, 7 electrons in the outermost layer for the fluorine. All right, for chlorine, its configuration is 1s2, 2s2, 2p6, 3s2, 3p5. So the third energy level is the highest, and there are 1, 2, 3, 4, 5, 6, 7 electrons there. Bromine. Now, I gave you a noble gas configuration. Its full electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p5. The highest energy level here is the fourth energy level. And again, there are 1, 2, 3, 4, 5, 6, 7 electrons in that outermost energy level. All right, same with iodine. Now, it's not that every atom has 7 electrons in the outermost energy level, but it just so happens that all of these elements are in the same column of the periodic table. And because of that, all of their electron configurations end the same, and they all have the same number of valence electrons. Okay, here's a little reminder of that. Remember this chart right here with the sublevel blocks? Take a look. Fluorine, chlorine, bromine, iodine. All right, these guys right here. All right, right here. All of their electron configurations end in something S2, something P5. So they all have 7 outer electrons. But that's just these guys, okay? Different columns have different numbers of valence electrons. So for example, column 1, everything in column 1 has 1 outer electron. Everything in column 2 has 2 outer electrons. Skip this middle portion, that's 10 atoms wide, all right? Column 13, everything here has 3 outer electrons. 4, 5, 6, 7. Column 18 has 8 outer electrons, except for helium, which only has 2. All right. So to figure out how many outer electrons an atom has, I'm not asking you to like completely rewrite its electron configuration, right? Just look at this chart. But know that the reason for this, the underlying reason for this, the reason why everything in column 17 has 7 outer electrons is because they have a similar electron configuration that all ends in essentially the same layout. Okay, so that's where that comes from. Now, having you people in class, we picked out a few valence electrons here. So sodium is Na. It's in the first column, so sodium has 1 valence electron. Carbon over here is in column 1, 2, 3, 10. Let's see here, 10, 11, 12, 13, 14. Carbon is in column 14, so it has 4 valence electrons. Okay, neon and xenon are both in the very last column, so they both are in column 18. They have 8 valence electrons. Okay, very good. Now, all of these atoms are most stable when they have 8 outer electrons. 8 is the most that the outermost energy level can hold, and atoms are most stable when they have 8. This is called the octet rule, okay? This is when atoms have a full S and P sublevel in the outermost energy level. Okay, now, again, there are some small atoms that can't fit 8 electrons in their outermost layer. Helium, hydrogen, helium, lithium, they only need 2, but the vast majority of atoms are trying to get 8 electrons in the outermost energy level. Only the noble gases, only the last column on the periodic table has 8 of these outer electrons. So they're comfortable. They don't ever need to bond or do anything. They can just float around being totally content and stable and having 8 outer electrons. Every other atom, though, wants to get 8 outer electrons. So how do they do this? Well, we got a problem here, okay? We got a problem. You could say, oh, this atom is only 2 electrons away from having 8. Maybe it has 6 on the outside and it wants to steal 2 more. Well, remember that atoms are also most stable when they are neutral, when they have the same number of protons as they do electrons. This creates a problem. How can an atom balance its desire for 8 outer electrons without creating an imbalance, all right? Without creating an imbalance. So look at it this way. Here's an oxygen atom, okay? It has 1, 2, 3, 4, 5, 6. It has 6 outer electrons. Now it wants to have 8. It only has 6. It could steal 2 electrons, but as soon as it steals 2, now it's not neutral anymore. It would have a -2 charge. Okay, so you can't just steal electrons without consequence here. So how do atoms deal with this problem of trying to get 8 outer electrons while still maintaining a neutral charge? Well, what they do is they bond. Atoms bond. Bonding is the process where atoms share and steal electrons from each other to gain an octet. This is why atoms bond. This is why there's so many molecules out there, okay? Right now I'm looking at a couple of candles on my table, right? They're made of wax. These atoms did not bond to form wax. They bonded to get a stable number of outer electrons. The fact that they formed wax is just a byproduct of them trying to become more stable, okay? So this is why complex substances like molecules and compounds exist. Atoms are trying to connect to become more stable. All right, and now there are different ways that atoms can bond depending on the type of atom. All right, different atoms are going to bond differently. Let's take a brief look at this, okay? So first you got metals. Metals are all of those elements, all those types of atoms on the left of the periodic table. Anything in red down here is a metal, okay? Metals are malleable, all right? They're bendable, they're shiny, they conduct electricity. You know what metals look like. They all pretty much look like that, various forms of shiny gray solid things. There's a few, there's gold and copper, they're a slightly different color, and mercury is a liquid, but almost every single metal looks pretty similar. Some a little lighter, like lead, or like aluminum, some a little darker, like lead, all right? Now, 80% of the elements that exist are metals, all right? Including all those elements on the bottom of the periodic table that we never really talk about. They're all metals, okay? And what these metals have in common is that they have very few valence electrons. They have very few outermost electrons. So for them, the easiest way to get 8 electrons in their outermost energy level is to get rid of electrons. These elements all give up electrons when they bond in order to get 8 outermost electrons. Now maybe you're asking, Mr. Gucci, how can an element or an atom gain 8 outer electrons? How can it get 8 outer electrons? By giving electrons up. Well, let me show you. Let me draw it for you. And I'll use magnesium as an example, okay? Magnesium is an atom with 12 electrons, okay? Its electron configuration is 1s2, 2s2, 2p6, 3s2. Okay, there we go. Now we see here that this atom, the highest energy level, is energy level 3, and it's got 2 electrons there. Okay, let me draw this out for you. Here's the nucleus of magnesium. The first energy level has 2 electrons. Okay. The second energy level has 1, 2, 3, 4, 5, 6, 7, 8. 8 electrons. The third energy level just has these 2. All right? So if it wanted to get 8 outer electrons, I guess it could go and steal 6 more. All right? But that is a hassle. It would be a very unstable way to go about solving this. What the magnesium atom does instead is it just tries to get rid of these 2 on the outside. Get rid of them. Be gone. Because as soon as you can get rid of them, what you have left underneath is 1, 2, 3, 4, 5, 6, 7, 8 electrons. So metals only have a few electrons in their outermost energy level, so they're going to try and get rid of them. Because if they can, then that exposes the level underneath, making it the outermost layer where they have 8 electrons. It's kind of like how, if you're cooking, if you're cooking a dish that requires onions, sometimes the outermost layer of the onion is rotten. And it'd be really hard to try and fix that outermost rotten layer of the onion. So what do? You just tear it off and throw it away, and what you're left with is the pristine onion layer underneath. Okay, so it's kind of like that. That's how I look at it. Okay, so that is how metals gain an octet. All right, how about the other elements called nonmetals? All right, so metals are all those elements on the left of the periodic table. Okay, the nonmetals are all the elements on the right of the periodic table. They are the dull, non-malleable, non-conductive elements like carbon or sulfur or phosphorus, all right? Or antimony, all right? Is that there? No, selenium, all right? Most of the nonmetals are actually gases, okay? But what they all have in common is that they all have many outer electrons, 5, 6, 7, or 8 outer electrons. So these guys are pretty close to getting 8 outer electrons. So what they are going to try to do is they are going to try and steal electrons while bonding, okay? Metals will give up electrons while bonding. Nonmetals will steal electrons when bonding, okay? And so these different elements act differently. Now, the easiest way, by the way, here's a little thing here real quick. All right, let's take a look here. So let's identify these metals, or these elements as metals or nonmetals. Sodium. Is sodium a metal or nonmetal? Well, sodium is Na, so it is a metal. Sodium is a metal, all right? Is carbon a metal or a nonmetal? Carbon is element C. Here's carbon. Carbon is a nonmetal. In fact, most of the elements that are used to make complex molecules, like the ones that make up DNA, the elements to life, they are all nonmetals, okay? Is silicon a metal or a nonmetal? Silicon is Si. Well, we see here that it's not a metal or a metal. It's a metalloid. It falls in between. It falls in between. So if everything on the left is a metal, if everything on the right is a nonmetal, those that fall on this dividing line are somewhere in between. They're shiny like metal, but they're brittle like nonmetal. They're kind of like a glass type consistency. Like silicon is like a dark bluish purple gray, like a particular metal perhaps, but it flakes off. It doesn't conduct electricity. It's not bendable. All right, so metalloids are in between, and because of that, we're not really going to talk about them that much. Okay, so how does bonding work now? Well, metals want to give up electrons. All right, that's the easiest way for them to get an octet. Nonmetals want to steal electrons. That's the easiest way for them to get an octet. So a natural type of bonding that can occur is called ionic bonding. That's when a metal and a nonmetal get together. The nonmetal steals electrons from the metal. And so as a result, both of them get an octet. The metal becomes positive, The nonmetal becomes negative because it gained electrons, right? Metal becomes positive, it lost electrons. The nonmetal becomes negative because it's stolen, gained an electron. Now this creates a problem because now these atoms have a charge and they don't want to charge. What do? What they do is they now stick to each other. One is positive, one is negative. And so to help cancel the charges out, they stick to each other, and that sticking to each other is called ionic bonding. Here's a little picture that illustrates it right here, okay? So here's the sodium with one electron on the outside, and it gives it to this fluorine, all right? Now take a look. As a result, both of them now have 8 outermost electrons, all right? But now the sodium is positive because it lost an electron, and the fluorine is negative because it gained an electron. And because they have these opposite charges, they will now stick together. This is an example of ionic bonding. It's what we're going to be working on in the next chapter in chemistry, all right? What we're working on this chapter, though, is another type of bonding. We're working on a type of bonding called covalent bonding. Covalent bonding is when you get two nonmetal atoms together and they share a pair of electrons. They share electrons in order to get an octet, to get 8 outer electrons, all right? The reason is because, again, nonmetals are really, really close to having 8 outer electrons. They're so close that their pull on electrons is extremely strong. There's no way that you're going to pull an electron off of a non-metal atom easily, so no one's going to be stripping electrons off of anyone else. So what they do is they overlap each other, all right? This is, covalent, all right? Co meaning together, valent meaning valence or outer electrons. They share their outer electrons, kind of like a timeshare. All right, or like, okay, getting a little personal here. My parents were divorced, so I needed to be spending my time at different houses during the holidays. All right, no parent got me all the time. Both my parents, I assume, love me very much. All right, so they both want to spend time with me. So what do? Well, I spend Christmas Eve with my mom and Christmas Day with my dad. Okay, I would split my time between the two, and so my parents' lives would overlap in that portion, and then they would share me during the holiday season, and my siblings, I assume, as well. I guess they love my sisters also. Sure, why not? Okay, this is the strongest type of bond. All right, it is the strongest type of bond because it involves the atoms actually overlapping, and atoms can form multiple covalent bonds at once, right? Just like a complex family, I guess, might have to split up multiple Christmases in different locations if you have step siblings or something like that, okay? So here's an example of how this works, okay? So take a look in the left here, okay? We see a hydrogen and an oxygen coming together, and we see this hydrogen, it looks like, gives up an electron to the oxygen, but that's not what's really happening. Take a look on the right here. What's happening is that these atoms are actually overlapping each other. And so as these electrons zoom around, sometimes they're going to zoom around the hydrogen, sometimes they're going to zoom around the oxygen, but every atom gets to feel like it has a full outer energy level because they are overlapping. Okay? So here's a question for you. All right? Are the following compounds covalently bonded or ionically bonded? And the way you figure this out is are there any metals? All right, if there's metals and nonmetals, then it's ionic. Ionically bonded means it has metals and nonmetals. Covalently bonded means it's just nonmetals. Let's look at the first one here, magnesium chloride. It's got magnesium, Mg, which is a metal. It's got chlorine, Cl, which is a nonmetal. Metal and nonmetal, this first one is ionically bonded. It's an ionically bonded compound. How about this one? Carbon and hydrogen. This is C3H8, tricarbon octahydride, all right? Also known as propane, the same gas you use to grill with, okay? So carbon is a nonmetal. Hydrogen is a nonmetal. So nonmetals, this is a covalently bonded compound, all right? Lastly, iron oxide, okay? Iron, Fe. Well, I mean, it's iron, guys. It's a metal. But here it is. It's a metal. Iron is a metal. Oxygen is a non-metal. Y'all know oxygen. You breathe it. It's not a metal. It is a non-metal. So metal and non-metal together make an ionic compound. And that's your note, guys, all right? Good luck with your homework. I'll make a little help video for that up next, all right? Good luck, everyone.